So far we have discussed about Fourier series and how to write the Fourier series of a general periodic function. Okay, so what is it? It is actually f of x is equal to a0 plus sigma n is equal to 1 to infinity an cos n pi x by L plus bn sin n pi x by L. Okay, where actually the value of a naught is 1 by 2L integral given interval, that is c to c plus 2L f of x dx. Okay, and then integral an is equal to 1 by L c to c plus 2L f of x into cos n pi x by L dx, where this L 2L is taken as the given interval length. Okay, so the given interval is taken as 2L. Okay, so when you are being asked to expand a function as a Fourier series, you need to find out the values of a naught, an and bn. Okay, so that was the method which we adopted. Now we will discuss methods in which you can actually simplify these computations. Okay, we will discuss some easy ways to reduce the amount of computation. Okay, so that is where this half range series will come into picture. Okay, so before we discuss half range series, you know that if your interval is actually from minus L to L, okay, and suppose your function f of x is defined in the interval minus L to L, and suppose your function f of x is an odd function, you can see that the values of a naught and an will be 0 because of the property of odd function. Property of odd functions, the values of minus L to L, a naught and an will be 0 because minus L to L f of x dx, which is the value of a naught, will be 0. Similarly, f of x into cos n x n pi x by L, that is also an odd function. So when you integrate from minus L to L, the values of a naughts and ans will become 0, only bn will be remaining. Okay, so that is the ease of computation in the case of an odd function. Okay, suppose your function is an even function, what happens is that your a naught will be there, an will be there, but your bn would be 0. Why? Because in the formula for bn you have f of x into sin n pi x by L, and since f of x is even, f of x into sin n pi x will be an odd function, and therefore it will also become 0. Okay, so if the function is an odd function or even function, the Fourier series computations would be simplified and the Fourier series expansion would be much simpler. Okay, now we will use this idea to simplify the Fourier series computation of a general function. Okay, so we will see how to use this idea here. Okay, so I hope it is clear. So when you are given a function f of x and when you are being asked to expand that function in a given interval, suppose your interval is of length L. Okay, so I am just taking the interval length as L here. Okay, so suppose you need to find the Fourier series of this function in this interval, you need to find out the values of a naught, an and bn. Okay, this need not be an even or odd function. Okay, but the idea what I do is that suppose I am being given an function in the given interval of length L. Okay, I will extend this function, okay, which is defined in the interval 0 to L to the interval 0 to minus L. Okay, so I will extend this function which is originally defined here to this here also. I will extend this function from 0 to L to minus L to L. Okay, so how can I extend? I can extend it in two ways. Okay, I can either extend this function as an even function. So when it is an even function, it will be symmetric about the y-axis. So when I can extend this as an even function, or I can extend this as an odd function. In that case, it will be symmetric about this origin. Okay, so I will extend this function as an even function or an odd function. So if I can extend this as an even function, and if I find the Fourier series expansion of the function over the whole interval from minus L to L, okay, that expansion would be valid over the entire interval, and also if it is an even function, it will only contain a naughts and ans. Okay, so it is easier to compute rather than finding both a naught, an and bn. Or if I am extending it as an odd function, my Fourier series computation would only contain this bn, so it is much easier now. Okay, instead of finding all the a naughts and ans and bns directly, I will extend the function to a bigger interval. I will find a Fourier series expansion which is valid for the bigger interval, and therefore it is also valid for the smaller interval. So that is my idea. Okay, so when you are given a function, there are three ways in which you can extend it as a Fourier series. One way is a direct approach. You take the given interval 0 to L, you just find out the values of a naughts, an and bn. Okay, so when you do this method, remember this interval length is taken as 2L. So here in this case, the entire interval length is taken as 2L, where L is there in our expansion. Okay, your L will be actually L by 2, and in your expansion there is a naught plus sigma n is equal to 1 to infinity an cos n pi x by L, where this L is actually the half of the original interval length, just like our usual problems. Okay, so this is one way. Okay, another way is that I will extend this as a even function. Okay, for example, if I extend this as an even function, what will happen is that the function will be symmetric about the y-axis. So I need to extend this. My interval is actually 0 to L. This is the original function which is defined in the interval 0 to L. I'll extend this interval to minus L to L as an even function. Okay, so what will happen? So what will happen in this case? So in this case, your 2L is actually now 2 capital L, because this is the bigger interval. This is the interval which I am considering here. So actually 12 is actually your capital 12, or your L is actually the given interval length. So when you are doing like this way, when you are extending this interval in this way, the given interval length is taken as L. In the usual case, the given interval length is taken as 2L. So don't forget that it is very case, because in this case you are actually extending the interval to twice its sides. So your given interval length will be actually be L. Okay. So when I extend this way, what will happen? My expansion will become f of x is equal to a naught plus sigma n is equal to 1 to infinity a n cos n pi x by L, because your bn will become 0, because your function is now defined as an even function. So it is extended as an even function. Okay. So what will happen? Your value of a naught would be, it was actually 1 by 2L integral, now it is from minus L to L f of x dx, or in other words it is actually simply be a naught is equal to 2 times 1 by 2L, okay, integral 0 to L f of x dx, or simply 1 by L integral 0 to L f of x dx, 1 by L integral 0 to L f of x dx. And similarly, what will be your an? Your an is also again from 1 by L, okay, it is from minus L to L, okay, f of x into cos n pi x by L dx now. But since the function is even, because f of x is even, cos is even, so the product will be even, this will become 2 by L, okay, so it will become 2 by L into integral 0 to L f of x into cos n pi x by L dx. Okay, so also your bn will become 0. So this is basically called the Fourier cosine series, because it contains only cosine terms. So this is called the Fourier cosine series. Okay, we will also call it as the half range series. Okay, why? Your given interval is taken as a half range and it is extended to a full range. So that is why this is also called a Fourier half range series. So I can ask you expand the function as a half range cosine series, or simply they can ask you expand the function as a cosine series. Okay, so what is a Fourier cosine series? Is nothing but a naught plus sigma a n cos n pi x by L. Your value of a naught is this one. You just remember the concept, because you can always derive it from the original Fourier expansion itself. Okay, so this is the value of your a naught and this is the value of your a n. Okay, so let us expand once again. So this is the case here. So this is the Fourier cosine series. Okay, so this is the value of f of x and this is the value of a naught and b. So in this case, the given function which was defined over the interval minus L to L is actually expanded as a even function to the interval minus L to L and expanded. Okay, so your given, in this case, your given interval length is actually taken as L here. Okay, in the usual case, the given interval was taken as 2L, but in this case, actually you are extending it to minus L to L, thereby making the given interval length as length L. Okay, so that is the only difference which you have in the original case. Okay, using the same concept, you can also extend this function as an odd function also similarly. Okay, so you can also extend this as an odd function. In that case, what will happen is that your a naught will become 0, your a n will become 0, and you will only contain b n. It will be called the Fourier sine series. Okay, for example, so suppose this is, I am extending this as an odd function. What will happen is that now it is being defined as interval minus L to L. So your b n is equal to 1 by L integral minus L to L f of x into sine n pi x by L dx. So it will become simply 2 by L integral 0 to L f of x into sine n pi x by L, because this function is an even function, because f of x is odd, sine is odd, so the product will be odd, product will be even. Similarly, your a naught, it was from minus L to L f of x dx, it will become 0 because f of x is an odd function. Similarly, your a n is also 0. So your expansion will only contain sigma b n sine n pi x by L. Okay, so this is your Fourier series expansion. In this case, it contains only sine terms, so it is also called the Fourier sine series or the Fourier half range sine series. Okay, so I hope it is clear. So for your examination purpose, they will just give you a function, they will just ask you to expand the function as a Fourier cosine series or a Fourier sine series. So what is the Fourier cosine series expansion? Fourier cosine series expansion is nothing but a naught plus sigma a n cos n pi x by L. What is the Fourier sine series expansion? It is nothing but simply sigma b n sine n pi x by L. Remember, this L is the given interval length, unlike the usual cases. So only this much is required for you. The proof and everything is not required, which I have already explained all to you, but this is the only thing which you have to study, which is the expansion. So this is the Fourier cosine series expansion because it contains only cosine terms, and this is the Fourier sine series expansion, which is because it contains only sine terms. Okay, so we'll now do some problems based on this. Okay, so look at this function here. Expand this function as a Fourier sine series in the interval 0 to pi. Okay, so remember, the given interval length is actually pi, so it is taken as your L. So your L here is actually pi. In the usual problems of Fourier series, the given interval length is always taken as 2L, but in half range series or sine series or cosine series, the given interval length is actually taken as L, because you are actually extending that interval to 2L. Okay, so that is the reason here. Okay, I hope it is clear. Okay, so your L is here. So what's your Fourier sine series? It is nothing but it is f of x is equal to sigma n is equal to 1 to infinity bn sine n pi x by L. So in this case, your L is pi, so it is simply sigma n is equal to 1 to infinity bn sine nx. Okay, and what's your value of bn? Bn is equal to 1 by pi, that is, no, 1 by, this 2 by pi, because you are taking the interval minus L to L, so it is 2 by pi integral 0 to pi. Okay, and what is your f of x? F of x is actually pi x minus x square into sine n pi x by L dx, but your L is actually 1, so it is sine nx dx. So this is how you calculate the value of df. Okay, so just calculate it, please do it in the, what is it? Actually it will become 2 by pi, again pi x minus x square into, again minus cos nx by n, okay, minus pi minus 2x into minus sine nx by n square, okay, plus minus 2 into, again cos nx by n cube. Substitute the value from 0 to pi. So just substitute. When it is pi, this will become pi square minus pi square, this factor will become 0, again sine n pi is 0, this factor will become 0, only this will be there. So it is 2 by pi into minus 2 into cos n pi by n cube. Okay, now substitute the value of 0, this will become 0, this quantity will become 0, this will become simply plus 2 by n cube. Okay, so I think it is minus 4, so it is become plus 2 by n cube. So this will become 2 by pi n cube into, or 4 by pi n cube into, the cos n pi is minus 1 raised to n, already 1 minus sign is here, so it will be minus 1 raised to n plus 1, okay, plus 1. Okay, so it is actually 4 by pi n cube into minus 1 raised to n plus 1 by plus 1. So you can also simplify it if you want. You can give the condition in this odd or even, but it is not necessary, that's it. So your expansion will simply become sigma bn sine n pi x by L. So just substitute the values, that is your Fourier sine series. Okay, so in examination the question will be expand the given function as a Fourier sine series or expand the given function as a Fourier cosine series. Okay, so this is the calculation here. If you want, you can just check it out. Okay, so that's it. Okay, and again we'll do one more problem. Expand f of x is equal to e raised to minus x as a Fourier cosine series. So what is your L here? Your L here is the given interval length, which is nothing but pi. The Fourier cosine series is f of x is equal to a naught plus sigma n is equal to 1 to infinity a n cos n pi x by L. In this case, since your L is pi, it is a naught plus sigma n is equal to 1 to infinity a n cos nx. Okay, and what's your value of a naught? A naught is actually equal to, it is 1 by 2L, but since you are taking from minus L to L, it will be 2 by 2L, so it is actually 1 by L. Okay, 1 by L into integral 0 to L f of x dx. So in this case, it is actually 1 by pi integral 0 to pi. The value of f of x is e raised to minus x dx. So just substitute. So it will be 1 by pi into e raised to minus x by minus 1 in the limit 0 to pi. So it is 1 by pi into minus e raised to minus pi, okay, plus 1, okay, 1 minus e raised to minus pi. So it is just, okay, 1 minus e raised to minus pi. Okay, now what is the value of your an? An is actually it will become 2 by L integral 0 to L f of x into cos n pi x by L dx, but in this case it is actually 2 by pi integral 0 to pi f of x into cos, f of x is actually e raised to minus x, so it is actually e raised to minus x into cos nx dx. Okay, so it is 2 by pi into integral 0 to pi e raised to minus x into cos nx dx. Remember the formula of e raised to ax by ax into cos bx integral formula, so it will become 2 by pi. Use that formula here, it will be e raised to minus x by 1 square plus n square into minus cos nx plus n sin nx. So just remember the formula of e raised to ax into cos bx dx. So I have used this formula here. We have already discussed the formula in the previous sessions. So just remember those formulas. When we substitute the values here, your cos n pi will be minus 1 raised to n. Your sin n pi will be 0. Again sin 0 will be 0. Just substitute the values and find the value of a n. The calculation is done here. Okay, so this is the value for a n, and this is your Fourier cosine series. Okay, so simple problems will be only asked just to expand a function as a Fourier cosine series, or a Fourier sine series, or a Fourier half range cosine series. Everything is just the same. So this is coming from basically the Fourier series expansion itself. Only thing is that you have made the expansion simpler by including only cosine terms or just the sine terms. Okay, if you want, you can do some more problems also. You can try this problem also. Expand f of x is equal to a Fourier x in the interval 0 to as a Fourier sine series, cosine series. Sine series I will do, it's very simple. Your given interval length is taken as L, so it is 2 here. Okay, what's the Fourier sine series expansion? It is f of x is equal to sigma n is equal to 1 to infinity bn sine n pi x by 2. Okay, so what's your value of bn? Bn is equal to 2 by L, it is 2 by L integral 0 to L f of x into sine n pi x by L dx. So in this case your L is 2, so it is actually 2 by 2, so it is 1, so it is actually integral 0 to 2 x sine n pi x by 2 dx. Substitute the value, so it will become x into minus cos n pi x by 2 divided by n pi by 2 minus again derivative of x, which is 1, again derivative of cos n pi x by 2, integral of cos n pi x by 2, it is minus sine n pi x by 2 divided by n pi by 2 the whole square. Substitute the value from 0 to 2 here. Okay, so this will become plus here, so this will become minus. So when you substitute 2, it will be, I think it is minus 2, okay, cos n pi 2 by 2, so it is just cos n pi by n pi by 2, right? Okay, plus again sine n pi 2 by 2, so it will be sine n pi, so it will become 0. Again when you substitute the value of 0 here, this will become 0. When you substitute the value here, it will be sine 0, again it will be 0. So this is the only thing, so it is minus 2. You can take 2 top to the numerator here, so it will be minus 4 by n pi cos n pi, or it is minus 4 into minus 1 raised to n by n pi. So that's the value of your a bn's here. So for the sine series will be simply be sigma bn sine n pi x. Okay, so n pi x by 2. Similarly, you can try the expansion of Fourier cosine series also. Please try that also. It's very simple, straightforward calculation. Okay, so please try that also. So as it is here, it is minus 4 by n pi cos n pi. Okay, similarly we can also expand this function as a Fourier cosine series. Please find the values of a nodes and a n's also we have done it here. Okay, so I hope it is clear. The Fourier half range series is very simple, just the Fourier series expansion. Only thing you have to remember is that the given interval length here is taken as L here. In this case, the Fourier series, the given interval length is taken as 2L. Okay, that's the only difference. The idea is because you are actually extending the given interval length into twice its size. That's why you are taking the given interval length as just L. Okay, similarly you can do this problem also. Here they have not asked you to find the Fourier sine series or cosine series expansion. They have just asked you if f of x is equal to this, show that this is the reason here. It's very simple. If you look at this expansions here, the first expansion will only contain sine terms. So this is actually your Fourier sine series expansion, and the second expansion only contains cosine terms. So this is actually your Fourier cosine series expansion. So just expand this function as a Fourier sine series and also Fourier cosine series and see what you will get. See whether you are getting this value also. Okay, it's very straightforward calculation. It's very simple. If you want to expand this as a Fourier sine series, the given interval length is actually pi. So your L is actually pi. And what's your formula? It is actually sigma bn sine n pi x by L. So it is nothing but sigma bn sine nx in this case. So what's the value of bn? Bn is actually 2 by L, which is 2 by pi integral 0 to pi f of x into sine nx dx. In this case it is x from 0 to pi by 2, it will be x into sine nx plus pi minus from pi by 2 to pi minus x into sine nx dx. just substitute the values and see that whether you are getting this value. Okay. Similarly, you can also go for Fourier cosine series also. Just straightforward computation, nothing new is there. All these type of problems are already done in your Fourier series expansion. Okay. So that's all. Thank you.